Hi everyone, this is NLP Corgi. Today's deep dive is about the paper from Beihang University. Weak-driven learning, how weak agents make strong agents stronger. This work starts from a simple observation. Most of our progress with large language models now comes from post-training, things like supervised fine-tuning and knowledge distillation. But as models get better, these methods run into a ceiling. The model becomes very confident, gradients vanish, and extra training barely helps. Instead of asking for ever stronger teachers, this paper flips the story. It introduces WMSS, a weak-driven learning paradigm where weaker checkpoints of the same model are used to push an already strong model even further. Under standard supervised fine-tuning, the model quickly learns to strongly favor the correct token over all others. Early on, the logit margin between the correct answer and distractors grows fast, but after a few epochs, that margin stops increasing. At that point, the model's decision boundary is effectively frozen. Gradients on incorrect tokens shrink towards zero, so the model no longer gets useful signals about how to separate subtle but plausible mistakes from the true answer. This is the saturation bottleneck the authors focus on. The core insight is that earlier, weaker checkpoints still remember uncertainty and confusion that the final model has largely suppressed. Those weak states assign more probability to plausible but wrong answers. By comparing a strong model to its weaker self, we can identify where the strong model has become overconfident or brittle. Instead of imitating a better teacher, the strong model learns by pushing away the specific mistakes that its weaker self still finds attractive. That disagreement becomes a rich source of training signal, even after standard supervision has saturated. Formally, weak-driven learning is any post-training setup where a strong model is improved using its discrepancies with a weaker reference model. You start with a strong agent and a weak agent, often just an earlier checkpoint. For each training example, you look at both outputs together and build a new supervision signal from that pair. Training then updates the strong model into an even stronger version, without ever needing a larger or better external teacher. WMSS is a concrete implementation of weak-driven learning. It runs in 3 phases. First, you train a base model with standard supervised fine-tuning to get a strong checkpoint, and you keep the original base as the weak agent. Second, you build a curriculum that selects the most informative training samples, based on how the weak and strong models' uncertainties change. Third, you jointly train the 2 models by mixing their logits and backpropagating through this fused distribution, which systematically amplifies gradients on hard negatives and pushes the strong model beyond its previous plateau. The initialization is simple and practical. You begin with a base model, call it M0. You fine-tune it with ordinary supervised training to obtain M1, which is your current strong model. Then you freeze the roles. M0 becomes the weak agent, preserving its softer, more uncertain decision boundaries, and M1 becomes the strong agent that you want to further improve. No extra models or external teachers are required. Next, WMSS decides which training examples are worth revisiting. For each sample, it computes predictive entropy under both the weak and strong models. The weak model's entropy tells you how inherently hard the sample was. The change in entropy tells you whether the strong model has become more confident or it has actually regressed. WMSS then builds a sampling probability that combines 3 terms: base difficulty to keep hard examples in play, consolidation to revisit samples where the strong model learned too quickly and might be brittle, and regression repair to focus on cases where the strong model is now worse than the weak one. The 3 coefficients, alpha, beta, and gamma, control how the curriculum behaves. Base difficulty, weighted by alpha, ensures that samples the weak model struggled with remain emphasized. Consolidation, weighted by beta, catches cases where the strong model suddenly became very confident. These might be overfitted and need stabilization. Regression repair, weighted by gamma, is especially important. If the strong model is now less certain than the weak one, that's a clear sign of catastrophic forgetting or boundary drift, so those samples are heavily upweighted to repair the damage. In the final phase, WMSS turns weak-strong disagreement into a concrete training signal. For each input, both models produce logits over the vocabulary. These are linearly combined into mixed logits, controlled by a mixing coefficient lambda. The mixed distribution is then used in a standard cross-entropy loss against the ground truth token. Gradients flow back through the mixed logits into both models, but the strong model is the one we care about. Because the weak model assigns more mass to plausible distractors, mixing reintroduces probability on those hard negatives, which revives their gradients and lets the strong model keep refining its decision boundary. Mathematically, the gradient of cross-entropy with respect to a negative token's logit is just its predicted probability. Under standard SFT, once the model is very confident, those probabilities are tiny, so gradients vanish. The weak model, however, still gives non-trivial probability to hard negatives. When you mix logits, you shrink the margin between the correct token and these distractors, which increases their probability under the mixed distribution. That directly increases the gradient magnitude on those tokens, giving the strong model a renewed push to suppress them and sharpen the boundary. The authors describe the dynamics of weak-driven learning in 3 stages. Early on in stage 1, mixing with the weak model amplifies gradients on hard negatives, and the strong model dominates the effective update. As training progresses and the strong model becomes very confident, the softmax Hessian collapses, and the weak model receives little curvature information. This is stage 2, gradient shielding, where the weak model's influence on learning fades even though its logits are still mixed in. Finally, in stage 3, because softmax is invariant to global logit shifts, the system can drift along a flat direction in logit space, changing mean logits without affecting sharpness. This explains some of the logit statistics observed after training. Putting it all together, WMSS runs as an iterative loop. You start from the initialized weak and strong models. At each iteration, you compute entropy dynamics, build sampling weights, and draw an active subset of the data. Then for that subset, you run joint training. Forward both models, mix their logits, compute the cross-entropy loss, and update the strong model parameters. After several such rounds, you end up with a new checkpoint that is consistently stronger than what standard supervised fine-tuning alone would produce. To test WMSS, the authors fine-tuned several open models from the Qwen family, including 4B, 8B, and a 3B Qwen 2.5 model. They evaluate on a broad suite of math reasoning datasets, from competition-level AMI and AMC to GSM-8K and MOPS, plus 2 code generation benchmarks, HumanEval and MBPP. WMSS is compared against standard supervised fine-tuning, Undial, which perturbs target logits, and Neftune, which injects noise into embeddings. All methods share the same training budget and implementation stack to keep the comparison fair. The results show that WMSS reliably breaks the optimization plateau of standard SFT. For the Qwen 3-4B model, average math accuracy jumps from about 64 to 69%, and code accuracy rises from 63 to nearly 67%. For the larger Qwen 3-8B, the gains are even bigger. Math goes from roughly 67 to 73%, and code from 71 to almost 78%. These improvements come purely from better training dynamics. At inference time, you still use a single model with no extra cost. This table summarizes the core empirical story of the paper. Across 3 different base models, WMSS consistently outperforms standard supervised fine-tuning, Undial, and Neftune on both math and code benchmarks. The pattern is robust. Weak-driven learning delivers the best or second-best scores almost everywhere, especially on the hardest reasoning tasks. Looking more closely, WMSS shines most on the hardest problems. On AIM 2025, a very challenging math competition benchmark, the 4B model's accuracy jumps from 12.2 to 20%, and the 8B model climbs from 15.6 to 20%. On AMC 23 and Aqua, which are also non-trivial, WMSS recovers performance dips seen in standard SFT and pushes accuracy substantially higher. On easier datasets like MOPS, the models approach saturation without forgetting earlier skills, suggesting that WMSS acts as an adaptive regularizer rather than just adding noise. Compared to Undial, which directly penalizes the target token with random noise, WMSS takes a more principled route. The results show that Undial often degrades performance, likely because it weakens the main supervision signal. Neftune, which injects random noise into embeddings, can improve robustness, but doesn't know anything about the model's specific error patterns. WMSS, by contrast, uses the weak model's historical confusion to construct targeted corrections. This structured guidance is especially important for math reasoning, where WMSS clearly outperforms Neftune. When you track performance over epochs, you see a familiar pattern: rapid improvement at first, then a slow approach to a plateau. Interestingly, for some datasets like AMC 2023, performance actually drops after too many epochs, signaling over-optimization and forgetting. WMSS's analysis highlights this inflection point and shows that its curriculum and weak-driven updates help capture the gains before the model starts to regress, especially on the more fragile reasoning tasks. A key insight comes from analyzing how logits change. Under standard SFT, both the correct token's logit and the average distractor logits plateau, so the margin stops growing. With WMSS, the target logit only increases slightly, but the mean logit of non-target tokens drops dramatically, by more than 50% in one analysis. This suppression-dominant behavior effectively clears out background interference. Because softmax is exponential in the logits, even a modest linear widening of the target background gap translates into a much sharper probability distribution and better accuracy. The ablation study teases apart the contributions of each component, starting from standard SFT at about 54% average accuracy. Adding the curriculum alone bumps performance to 56.3%. Introducing joint training with weak and strong models raises it further to 58.2%. The full WMSS pipeline, combining both curriculum and joint training, reaches nearly 60% and almost doubles performance on AMI compared to the baseline. This shows that data activation helps, but the real breakthrough comes from systematically leveraging weak model signals during training. The authors also explore how sensitive WMSS is to its hyperparameters. For the curriculum, increasing the consolidation weight beta can boost performance on standard math problems, but if you turn off regression repair, hard benchmarks like AIME suffer. Introducing a modest regression repair term gamma significantly improves those challenging tasks, even if it slightly reduces scores on easier ones. For the mixing coefficient lambda, performance follows a broad inverted U-shape, with the best results around 0.42 to 0.48. Too close to 1 and you're basically back to standard SFT, too close to 0, and the weak model dominates, leading to underfitting. Under the hood, WMSS is trained on a carefully curated subset of the AM1.4M dataset, covering both math reasoning and code. For math, solutions are verified with a dedicated library to ensure correctness. For code, snippets are extracted and run against test cases, keeping only those that pass. The final dataset has about 215,000 high-quality samples. Training uses the TRL library and the Qwen3 architecture from Transformers, with long context lengths and a modest learning rate, all run on 8 H800 GPUs. Like any method, WMSS has limits. The experiments focus on math reasoning and code generation, which are structured and verifiable. It's not yet clear how well the approach transfers to open-ended dialogue or knowledge-heavy tasks. WMSS also assumes you have access to labeled data and to earlier checkpoints of the same model, which may not always be available. Finally, the curriculum and mixing coefficients need tuning to balance easy and hard tasks, so there's still some engineering overhead. Stepping back, the main message of this paper is that we don't always need stronger external teachers to improve large language models. The model's own weaker past selves already encode rich information about where it was confused and what mistakes it found plausible. WMSS shows how to turn that historical confusion into a structured training signal that breaks through the saturation of standard supervised fine-tuning. This opens a path toward more autonomous, data-efficient post-training, where stronger agents emerge by learning from their own weaker versions.